Welcome to Electrophoresis.
Hello, we are Group 11 and our video is going to be on gel electrophoresis. The objective of this experiment was to use gel electrophoresis to determine the identity, purity, and concentration of unknown protein samples. Gel electrophoresis is a laboratory procedure that allows for unknown proteins, DNA, and RNA to be separated and identified in relation to their molecular weights. In the process, samples are loaded into chambers within a gel, through which a current is then applied, resulting in an electric field. Samples either have a natural charge or, in our case, were given a negative charge through a denaturing process so that they will move towards the electrode with the opposite charge. The size and length of each specific compound determines how quickly it travels. Smaller and shorter molecules move faster than larger and longer ones. Because of this, if a known standard solution is loaded next to unknowns, the molecular weight of the unknowns can be found by comparing its RF value to that of the known standard. Once the molecular weight is known, the specific compounds present in each unknown solution can then be identified.
First, we set up the apparatus for creating the gels. This included a short and long plate as well as a clamp to ensure the plates were in place. These were tested using deionized water to ensure that there was no leaks when we began our gel process. For this experiment, we used CHEG stain-free acrylamide kit to create our gels. Before adding the gels, we marked a line that was 1 centimeter away from the bottom of the cone. This is where the resolving gel would be filled up to. First, we created a resolving layer by combining resolving solutions, APS and TMAN. The solution was then pipetted into the apparatus, covered with a layer of isopropyl alcohol, and allowed to polymerize for 90 minutes. After this time had passed, the IPA was soaked up using filter paper, and the stacking solution was made. This stacking solution was pipetted onto the resolving layer up to the top of the glass, and the cone was inserted. Then it was allowed 20 minutes to polymerize. Next, the preparation of the protein samples. The protein samples needed a negative charge so that they would move with the SDS page once in the electric field. Hence, they need to be denatured. This was done by adding lamella sample buffer solution and beta-markethanol to the samples. Note that beta-markethanol should be inserted into the protein using the biohood. After this process, the proteins are heated in a dry bath at 95 degrees Celsius for at least 5 minutes. Once this was completed and the gels were polymerized, the experiment could then run. The gels were inserted into the apparatus with a short plate facing the inside. The apparatus was filled with running buffer, and the combs were removed from the gel to create the lanes. The protein samples and the standard were then loaded into each chamber. The power supply at 200 voltage was connected and turned on, and the samples were run for 35 minutes. Once this was complete, the power was turned off and the gels were removed. Once the gels were removed and on the image tray, they were taken to be imaged so that data could be analyzed using the Image Lab software.
Unfortunately, our data for this lab was not usable due to issues with our gels. We believe the issues were related to the proteins possibly not being denatured for a long enough time, as well as broken micropipettes possibly affecting the volumes of the gel solution components. Dr. Pascal has provided the data that will be used in this section. 3 different gels were given to us, all showing nearly identical results to the one seen here. Using the Image Lab software, we were able to find the molecular weights of the bands in each lane. Each lane shown has bands in the same location, meaning that the same unknown sample was placed in each lane. 2 distinct bands formed with molecular weights of 29.16 kilodaltons and 31.68 kilodaltons. Using the volume intensities, we were able to find the purity of each individual band, which can be seen here. The equation to find these values is the volume intensity of a single band divided by the sum of the volume intensities across the entire lane. The Image Lab software automatically calculates these values. The volume intensity can also be used to find the concentrations of each protein by forming a calibration curve with the intensity on the y-axis and the mass on the x-axis. The mass used is of known protein samples, and when plotted, the linear equation for the trend line can be solved for to obtain the unknown protein masses. This answer is then divided by the volume of each sample placed in each lane to get the concentration.
As stated before, two distinct bands were found in each lane, signifying two different proteins present in each sample. Based off the molecular weights, we believe that the protein with molecular weight of 29.16 kilodaltons is casein. Casein has a molecular weight that can range from 25 to 29 kilodaltons depending on the type. We believe the protein with a molecular weight of 31.68 kilodaltons is carbonic anhydrase, which has a molecular weight between 30 to 32 kilodaltons. By accounting for the standard deviation for each band across all lanes, our predictions are reasonable. All the data we calculated can be found in the table on screen now. Thank you for watching.